Okay, so the last thing I want to mention is based on what went on with the midterm, it was clear that quite a few of you had a bit of trouble identifying what forces acted when and in what sort of conditions. And I realize if you look at the material, we sort of go through each force individually, but we have nothing that lumps them all together. So what I did is I played around with a flowchart thing, and I put together a sort of a flowchart which hopefully will give you some idea of what you should be thinking. Now, obviously, this is not something you will have in an exam, well, unless you somehow manage to transpose it onto the back of your formula sheet in tiny print. But the idea is to just give you some idea of what thought processes should be going through your head when you get to a question which says, you know, what are the forces acting on an object? Or if you want to know what the forces are acting in order to cause an acceleration. Because some of you were clearly sort of saying, oh, well, I must have a force here that's producing an acceleration, so I'll just add an accelerating force. And that's sort of the wrong way round of thinking. You should be thinking what forces are there, what's causing the forces, and then making sure that if you know an object's accelerating, at least one of those forces could cause the acceleration. And if you don't have a force that could cause the acceleration, that means somewhere you've missed a force, and you need to go back and think about the forces that are acting. So I don't pretend that this is a fail-safe thing that will solve every single problem for you and make sure you get everything right, but hopefully it will at least start you thinking in the right way. So you can download this from the website. It's a PDF. It's on the website under the Newtonian forces section. There's a little now orange section that says additional material, and you can download the PDF and print it out or read it online from there. So that's just to try and help you get into sort of the right mode of thinking when you see a problem with forces, and that'll be useful in the next section we do with equilibrium, because there you really need to identify all the forces when we start doing the more complex equilibrium problems. So that's just intended to help. Okay, so last time we ended up with a very quick skim through the proof of what we call the parallel axis theorem. So you can see it on the lecture notes. I'll be uploading. I know I'm a little bit behind with the lectures. I'm going to have several days on shift at CERN, and in the middle of the night there's not usually a lot to do. So that'll be when I'm updating all the lecture notes. So we went quickly through this proof here that showed that if you know the moment of inertia about an axis that goes through the center of mass of the object, and this can be any object, it doesn't have to be anything regular, it can be any object at all. If you know the center of mass about an axis through if you know the moment of inertia about an axis through the center of mass, then you can calculate the moment of inertia about any other parallel axis. It does have to be parallel. It can't be at any angle to it. It has to be a parallel axis. You can calculate the moment of inertia about any parallel axis by just adding on the mass, the total mass of the body, multiplied by the distance that this new axis is away from the center of mass squared, right? And so this is what we call the parallel axis theorem, and it allows us to calculate the moment of inertia about any other parallel axis once we know it about an axis through the center of mass. Now, if you don't know the moment of inertia through the center of mass, of course you can calculate it, because if you know the moment of inertia about some parallel axis here, to move it to the center of mass, instead of adding mr squared, you just subtract mr squared. Right? And so you'll see that in some of the assignment questions, and possibly on the exam if I ask it, right? You need to remember that this guy is the one through the center of mass, and if you're told a different moment of inertia, then you need to remember, you need to use this thing, but remember that this one is the one that goes through the center of mass, and rearrange the equation appropriately. Oops. Okay, so let's do a simple example. So here what we've got is we've got a moment of inertia. We want to know what is the moment of inertia of a dumbbell like this that's about an axis through its center of mass here, right? So what we can do is we know the formula for the axis, for the moment of inertia of a sphere about an axis through its center of mass. So if we take a sphere and we want to know what its moment of inertia is about a solid sphere about an axis that passes through the center of the sphere, then we can look up the formula, and it's 2/5 mr squared, right? So that would be a formula that you'd be given if this was a question in the exam, since you can't calculate that easily from first principles with the level of calculus you've got at the moment. So you'd be told that this is the moment of inertia of a solid sphere. Then we need to move this axis from here. We need to move it to here because we're rotating about an axis here, not about an axis through the center of mass of the sphere. And so we use the parallel axis theorem. If this is 1.5 meters, then this distance here is 0.75, so we add 0.75 squared times the total mass of the sphere, right? And we can stick all these numbers into our calculator, and we're not told what the, well, we can put the mass in later, but if we put in all these distances r here, then we can calculate that the total moment of inertia of this sphere about this axis here is 17.355 kilogram meter squared. So since we've got moment of inertia is a mass times a distance squared here, right, then we get units of kilogram meter squared. So just to reinforce that, I should have drawn this to start with. All we're doing here is we're taking the moment of inertia here about the center of mass, and since this dumbbell is rotating about this axis here that's parallel, we are moving this axis from there, from here to here, and so we're using the fact that the moment of inertia about this axis is equal to the moment of inertia about the center of mass plus m times r squared, right? So all we're doing is we're moving the axis of rotation from the center of the sphere to the center of the dumbbell, right? And clearly, exactly the same happens here. We have an axis through the center of the solid sphere here, and we're moving it all the way to this axis here, and it's going to be exactly the same. We're moving it through the same distance. The fact that it's on the opposite side doesn't matter. Moment of inertia is a scalar quantity, right? So we're going to end up with twice this value for the moment of inertia of both spheres. Okay, and then the final thing we have to add in here, of course, is the moment of inertia of the rod about the center. Well, we calculated that from first principles yesterday, and that was a 12th ml squared. So the length is 1.5 meters. We were told what the mass is in the question, and so again, we can calculate this quantity here entirely, and the total moment of inertia here, so this is how you build up a moment of inertia. It's a scalar quantity, so you just simply add moments of inertia. You will never have, just like you never have negative masses, you will never have a negative moment of inertia, right? It'll always be positive, and as long as you are adding moments of inertia about the same axis, and that's crucial, right? You can't add moments of inertia if they're not about a common axis. But if you remember, we moved the axis of the sphere, we moved it from through the center to the middle of the dumbbell. We're calculating the moment of inertia of the rod about an axis through its center, which is in the same location, and so we can add together, we just simply add together these scalar quantities that are the moments of inertia, right? But clearly we'd have got it wrong if we'd have just said, well, this is the moment of inertia of this sphere about this axis, and got 2/5 mr squared, and added it to the 12th ml squared here, right? Because that would be this axis here. We can't add it to a moment of inertia about this axis, right? We have to move this axis to there before we can add the moments of inertia. So we just add these three moments of inertia, stick the numbers into the calculator, and get 35.65 kilogram meter squared, right? But the crucial point here, and a place where quite a few people make mistakes on exams, is that they forget you can only add moments of inertia if they're about a common axis. So always make sure the moment of inertia is you're adding them about a common axis, because that's a common mistake. Okay, so now, once we've calculated the moment of inertia, we can go a little bit further. We can say, well, supposing we recreate the experiment that we did a couple of lectures ago where we had these two weights on the end and we rotate, we have a weight here that's acting on a tension and it's going to cause this object to accelerate. So what we've got now is we've got a slightly more complicated system. And we're going to attach a pulley or a wheel here. And we have our mass M hanging below. Now, so if I look at the forces here, right, well, I've got a weight acting on the mass, so that's an mg hanging down, and I've got a string, so I have a tension, and I have a tension acting upwards on this mass, and I also have a tension acting downwards here on this pulley where the string is wrapped around, or this wheel where the string is wrapped around it, and is going to cause it to pull down and make this turn. So, since I've got a force acting on this thing, I've got a pivot point here. So if I was wanting to add in all the forces, then there would also be an upward force at this pivot point acting on this dumbbell, right? Because the dumbbell itself does not accelerate in a linear fashion. It starts to turn. So if it's turning, then there must be a zero net force on it. If the center of mass of this thing is not moving, then the net force on this must be zero. So there'll be an upward force here at the pivot, which is why the thing does not have a linear acceleration. But clearly, since I've got a force here, if I take moments about the axis of rotation, then clearly I'm going to have a net moment acting on this dumbbell. Right? Because I've got a force, and it's acting at a distance away from the axis of rotation, and so I've got a force multiplied by this distance here will give me a moment, and that's going to cause, as we've seen where we did Newton's second law in the rotational form, will cause an angular acceleration. So this may not look like it, but this system is in fact very, very similar to the Atwood's machine. Right? You remember in the Atwood's machine we had this pulley here, and then hanging on the other side of it we had another mass. And we had to do Newton's second law on each of the two individual masses and use the fact that they had a common acceleration, and then we could solve for all the variables of the system. Well, here we're going to use exactly the same approach. We're going to use Newton's second law once here on this mass and once here on this rotating dumbbell. So first let's do it on the mass. Right? So if we use Newton's second law on the mass, we can take upwards as positive. Let's take downwards as positive. Right? Because the one thing I forgot to put on labels here is we've got an acceleration A downwards, and we've got an angular acceleration here of theta double dot. Right? So if I do Newton's second law downwards, I have the net force is mg, that acts down, minus t, because that's acting upwards, we're taking downwards as positive, and that is equal to the mass of this thing, that's m, times the acceleration a. Right? Now, what I'm going to do is take Newton's second law for the dumbbell, and here I've got to use the rotational form of it, because this object's rotating, it's not got a linear acceleration, and so I'm going to take anti-clockwise, or sorry, counterclockwise, as the positive direction, because that's the direction it's rotating in. So if we remember Newton's second law in the rotational form, its moment is equal to moment of inertia times the angular acceleration. So the moment of the force is equal to the moment of inertia multiplied by the angular acceleration. Well, the moment of this force here, right, if this distance here is r, right, then we've got the tension here acting a distance r away from the axis, and so therefore the moment is just t times r, because it's acting vertically down a distance r away from the axis. Right? So we have t times r, and it's acting downwards here, so it's going to try and make it rotate in the counterclockwise direction, and so therefore it's a positive moment. Right? So it's positive here. And this is going to be equal to the moment of inertia times the angular acceleration. So, if we look at this, we've now got a problem, because this is our first equation here, and we've got a second equation here, but we've got three unknowns. We have the linear acceleration of this mass, the angular acceleration of this dumbbell, and the tension in the string T. Now, and this is where it's a little bit trickier than the Atwood machine. With Atwood's machine, we had two accelerations each for the two masses, and we made the argument that each of those accelerations had to be equal to stop the string either snapping or going slack. Right? Now here, we're going to make the same argument, but obviously we can't just put a linear acceleration equal to an angular acceleration. We have to be a little bit smarter. So what we want to do is we want to look at the linear acceleration of the edge of this disk. Right? Now, since the string is stationary with respect to the edge of this disk, right, the acceleration of the string at this point must be equal to the acceleration of the string down here. Now the string here is accelerating with the same acceleration as this mass, because it's attached to it. And this piece of string is accelerating with the tangential acceleration of this disk. Right? And we know that the tangential acceleration is equal to the radius times theta double dot. And so the tangential acceleration of the string here, where it's in contact with the disk and has the same acceleration, must, by the same argument we use with Atwood's pulley, must be equal to the linear acceleration down here, because otherwise one end of the string is going to move away from the other, in which case the string has to snap, or what happens is one end is moving towards the other, and so the string goes slack and the tension disappears. Right? Neither of those are physical situations, so these two accelerations must be equal. So rather than saying that the angular acceleration is equal to the linear acceleration, it's this radius of this pulley here times the angular acceleration has to be equal to the linear acceleration. And then at this point now, we can solve the problem. We're asked what is the angular acceleration, so we want to get rid of this linear acceleration here. So if we go back to equation 1, then we can have mg minus mr theta double dot is equal to the tension. Right? So all I've done is I've put this expression here into equation 1 and got this equation here, and then I can just substitute that here into equation 2, so I can take this now and put it into equation 2, and what I'm going to end up with is mg minus mgr times mr squared theta double dot, because it's r times tension, is equal to I times theta double dot, and so therefore mgr is equal to theta double dot times I plus mr squared, and we end up with theta double dot is equal to mgr divided by I plus mr squared. Right? And so we can solve the equation, solve the problem, and then you just stick the numbers in and you'll calculate whatever comes out. That's done on the slide. So if you stick the numbers in, that 0.055 radians per second squared. Right? So that's how we can solve a problem like this. It's the same technique with Atwood's machine. We use Newton's second law on the two different objects, and we relate their accelerations to each other, and then we solve two simultaneous equations. Right? And if you look at this, you can actually get a little bit of a hint as to how you can as how you might have approached it differently, because if you look at this moment of inertia here, you'll see that this I plus mr squared is equal to the total moment of inertia of the system. Right? So if we treated this as a single system, this mass has a moment of inertia about this axis, and we could have actually treated it that way, and then the net force acting on the system is this weight here, and so we could have actually written it here. We have mg times r, well that's the moment of the weight about the axis of rotation of the system, and we could have pretended that this mass is rotating as well. Right? And that would have actually got us to the answer a little bit quicker, but you can't always do that. Right? It works in a simple example, does not always work. So you've got to be a little bit careful. Okay, any questions on that? Good, right? That's a typical sort of dynamics question that you'll have with rotating objects. Okay, so if you remember all the way back to the linear stuff, first of all we did linear kinematics, then we did linear dynamics, and then we went on to work and energy, right? And so we're working through the same sort of things now in rotational system, and so we have to worry about the rotational energy. Now, if you think about this example we just did here, right? You've got an object that's falling, right? So it's losing gravitational potential energy. There's no non-conservative forces acting on the system, so the total energy of this system has to be constant. But if we look at the linear velocity of both of these objects, you can see that this guy here is going to gain some linear velocity. But if you actually do conservation of energy on this and you calculate the linear velocity of this object, it's far less. The increase in kinetic energy here is far less than the loss in gravitational potential energy. But if we look at this system, this guy here has no linear velocity, and so therefore it has no linear kinetic energy. Obviously, though, if you look at this thing as it's rotating, this mass here is moving with a speed, and it's an increasing speed, and so is this mass. So it has to have some sort of kinetic energy, but it's clearly not a linear kinetic energy. And so we have to add in this concept now of rotational kinetic energy, right? So there's not just linear kinetic energy, we've got rotational kinetic energy as well. And so we need to have some way of defining what is the kinetic energy of rotation. Right? And in fact, this is something that's used in buses now to make them more efficient. Some cities, at least in Europe, are actually putting flywheels in the bus. And what happens is the bus charges up a flywheel, and when it slows, so it drives a flywheel, and the flywheel drives the actual wheels on the road. And what happens is when they brake, they can transfer the energy back into the flywheel and cause it to accelerate again. And so this is actually a sort of a mechanical way of storing energy, although now increasing battery technology is sort of making these systems rather obsolete. But they're still in use. The one place actually they used to be in use was and they may be using this big fusion reactor in ITER, but certainly the one that preceded it in Britain, the Joint European Torus, they needed so much energy in order to contain the plasma when they were doing a fusion test that the national grid couldn't provide that much power for such a short space of time, for a period of about 30 minutes. And so what they did was they continuously took power from the national grid system and spun up 4 enormous flywheels that were very, very heavily shielded, because if these things fail, they can destroy buildings. They've got so much kinetic energy in them. And then when they needed the power for the fusion tests, they basically used these flywheels to drive an electrical generator so they could get the energy back. And this was the only way that they could store such huge amounts of energy. So if you're wanting to store massive amounts of energy, flywheels are actually a good way to do it. Okay, so what we've got to do now is, if you remember before, what we worried about was we took a force acting on an object and we integrated and calculated how much work it had done, and that we put equal to the linear kinetic energy. So now what we're going to do is we're going to do the same thing, but we're going to do it for an object that's rotating. So here's our object here, and it's going to be a distance r away, and we're going to cause it to rotate round to another location, and we're going to have a force acting on it here, F, that's acting at an angle phi to the tangent, right? So this line here is a tangent. Now, we know from our definition of arc length that if this angle here is delta theta, right, then this here is just the arc length. That's the distance this mass has moved through. So that is just r delta theta, right? And so if we work out how much work this force has done, right, then, oops, I've labeled my angle wrong, beg your pardon. Right? Then if we want to know how much work this force has done, well, there's been no displacement in the radial direction, right? So no displacement in the radial direction, so no work has been done in that direction. We've only had a displacement in the tangential direction, so therefore the work done in moving this object through this angle of delta theta is going to be the distance moved, so that's r times delta theta, multiplied by the component of the force that acts in the direction of displacement, right? That's our definition of work done, right? It's the force dotted with the displacement. So it's this component along here, and if this angle here is phi, then the component that's tangential is f sine phi, right? So we can rewrite this now as f r sine phi delta theta, right? And that's the work done by moving this little force through this distance. But if we look at this, right, F times R times sine phi, this is just the moment of this force about the axis of rotation, right? It's the component of the force that's perpendicular to the line joining the axis of rotation to where the force acts. So this here is just the moment of the force. Right? So we can rewrite this now as the work done is just the moment of the force, the moment acting, times delta theta. Right? Now, what we're going to do is we're going to shrink things down because, of course, this moment could change. So you want to take an infinitesimally small period of time, so an infinitesimally small change, so the moment, we can treat the moment as constant for that tiny period. So what we want to do is we want to take the limit as delta theta goes to 0. And what this means now is an integrate, because we want to get the total amount of work that's been done. So we want to add up all of these little components of work, all of these little delta W's, but we want to do that over an infinitesimal period each time. So of course we're going to get an integration. And so what this gives us is it gives us the integration of dW is equal to the integral of n d theta. Well, the integration of all the little components of work, that's just the total work done. So therefore we get that the work done is equal to the integral of the moment with respect to the angle, right? And so that tells us that we can now at least calculate the work that has been done by a moment, right? So if we want to do that, all we do is we integrate the moment with respect to the angle turned through. So if the moment is constant, so then the work done is just n times the angle that the object has rotated through, right? So this is the angular displacement theta times the constant moment. But this only works if the moment is constant. If it's not constant, you have to integrate, which again is exactly like we did for force. If we had a constant force, we could just multiply it by the displacement. However, if we had a varying force, we had to integrate it with respect to the displacement. So you had to do the integral of f dot dr, right? So it's exactly the same here. We can multiply it if it's constant. If it's varying, we have to integrate it. So we've got the total work done, all right? So next thing we want to do is, now we know what the total work done is, right? We want to convert this into how much energy the system has, right? Because if we've got a moment that's acting on an object and causing it to rotate, the work that that moment has done, which we've now just calculated, has got to be equal to the increase in the energy of that object. And so that's how, if you remember, we got to the linear kinetic energy, and it's how we're going to get to the rotational kinetic energy, right? So we're going to have a moment now acting on an object, and we're going to start with Newton's second law in the rotational form. So we have Newton 2, right, is moment of inertia times theta double dot, and we're going to rewrite that as moment of inertia times d omega by dt, right? So that's just saying that our angular acceleration is the rate of change of angular velocity. Now we're going to write down our work done formula. And we're going to substitute this into here, right? So we're going to take, we know that moment is I times d omega by dt, and so we're just going to put this in here. So we end up with, it's equal to I times d omega by dt d theta, right? And again, we're going to do exactly the same trick we did with the linear kinetic energy, right? If you look at these guys here, this is equal to the integral of I times d theta by dt d omega, right? Well, this, of course, here is just equal to the angular velocity omega. So the work done is equal to the integral of I omega d omega, right? And this is exactly the same trick we used with the linear kinetic energy, only instead of theta we had x, and instead of omega we had v, and instead of I we had m, so we were integrating mv with respect to v. And so if we assume that we're going here from zero angular velocity when we're not moving, and we'll assume that that means we've got zero energy, up to some final velocity omega, then this is going to give us a half I omega squared, right? Because the second term will give us 0, so we're subtracting off 0. So what this means is that the work done in accelerating an object from 0 angular velocity up to some final angular velocity omega is a half I omega squared. And if that's the work done by a moment accelerating it, then that must be equal to the rotational kinetic energy that the object has, because we've got constant energy. So the result is that the rotational is equal to a half I omega squared. And so now we can calculate the rotational kinetic energy of an object using this formula, a half I omega squared. And we got the formula in exactly the same way that we got the linear formula for linear kinetic energy, right? Only we used rotational equivalence. Okay, so now, so any questions about that, right? It's a method you've seen before, just different variables. There's no difference to what went on, we just changed the variables. Good. So we've now got a formula for rotational kinetic energy. So when you're now doing constant energy, you're using energy to solve a problem, you also have to remember to include this if you've got an object that's rotating. So let's try an example. So here we're going to be having you betting on a horse race where the two horses are, one is a hoop, right? So this is a metal hoop, and this is a wooden disc. They both have exactly the same radius, and I haven't got some scales here, but they both have exactly the same mass. So they've got the same mass and the same radius, but one's a hoop and one's a disc. And so we're going to put them here at the top of this ramp, and then I'm going to release the gate, and they'll go racing down to the bottom. And the question is, which one will get there first? Will the hollow cylinder get there first? Will the solid cylinder get there first? Will they both reach the bottom at the same time? Or is there no way to determine which one will hit the bottom first? So what are the... Okay, so the bookie's favorite is A, with B and C being a close second. Okay, so let's see if I should have made the bet with you. Oh, we have a winner. So, okay, so just to show you that it's not a fluke, right? Because that should be every time you see an experiment and it runs once, your next question should be, let's see you do that again, right? right? Every single time, and I'll do it a third time just to convince you that it really is every single time. Right? So every time the disk will win. So why is that the case? Well, we just talked about rotational kinetic energy, right? So that should be a pretty strong hint as to what's going on. So if we look at these two objects, we've got one that's a loop, and we've got one that's a disk. Now, as we did last time in the last lecture, the moment of inertia of this ring is mr squared, where r is the radius. Right? And the moment of inertia of this disk is a half mr squared. Right? So this disk has got half the moment of inertia of the ring. You didn't have to know the exact formula. All you had to be able to recognize, and we did the question last lecture, so I was completely fair, you knew the answer, was that the ring here has a higher moment of inertia than the disk. Now, if you remember, if we're rolling without slipping, as we do down that ramp, then we have the linear velocity of the center of the circular object, whatever circular object it is. The linear velocity here is equal to r times the angular velocity, right? So if we look at these two guys here, so for rolling at the same speed, they will have the same angular velocity, right? So if the linear speed of these two objects is the same and they're rolling, they will have exactly the same angular velocity, right? Because they've got the same radius. But their rotational energy, kinetic energy, is equal to a half I omega squared. So if they are rolling at the same linear velocity, they will have the same linear kinetic energy, right? So in this case, a rolling object has both linear kinetic energy and rotational kinetic energy, right? So they will have the same linear kinetic energy, but because if we put this in here, right, we're going to end up with a half times I times r times v squared over, what am I doing? Okay, so here I have omega is equal to v over r, so here I have a half I times v squared over r squared, right? So if I have the two things rolling at the same linear velocity, their linear kinetic energy is going to be identical because it's the mass times the linear speed squared, so no difference there because they've got the same mass. But if I look at the rotational kinetic energy, their linear speed is the same, their radius is the same, but their moments of inertia are not the same. And so therefore, when you're rolling, this hoop that has a far larger, has twice the moment of inertia of the disk, this hoop has, for the same linear velocity when it's rolling, has more total energy. And since the energy that's driving this comes from the gravitational potential energy as they roll down the ramp, right, there is going to be the same energy available to both, but because to have the same linear speed, the hoop has to have a lot more energy, the only thing it can do is rotate more slowly, and so that's why it always loses the race. Because to move at the same linear velocity while rolling, it has to have more energy. There isn't more energy available, and so therefore it has to move more slowly, and so therefore the disk will always win the race, right? And so that's a little trick. That's a little bit hard to do at a bar, I suppose, and win money off your mates, but it's a little trick guaranteed to work every single time and confuse your friends with. Okay, so I skipped over that one. So here we can actually do the calculation, right? So if we look at this, we've now got the solid cylinder and the hollow cylinder. We've got the height difference here, h0. And so if we use constant energy, we have three energies that we have to worry about. We have the linear kinetic energy, the rotational kinetic energy, and the gravitational potential energy, right? So both of these are going to be the same. Both of these are going to be constant, and so here's our relationship, remembering for the linear velocity related to the angular velocity for something that's rolling that we covered several lectures ago. And so since your initial energy is equal to the final energy, you can put all of this in. These quantities, of course, are zero, and so you end up with mgh is a half mr squared omega squared plus a half I omega squared. So this is the linear kinetic energy, and this is the rotational kinetic energy, and this is the gravitational potential energy here. And so you can solve for omega, and you find that omega here is equal to the square root of 2 mgh over mr squared plus I. And since I is larger for the hoop, omega is going to be less, and so therefore its linear velocity is going to be less, right? So all the other quantities are the same for both of them. It's the moment of inertia that slows down the rolling hoop. Okay, so next question, which did I put that on a slide? I'll check. No, I didn't. Okay. So next question is supposing we were doing this experiment, but instead of rolling, we had them sliding. So we made this surface frictionless. Which would get to the bottom first then? So, oh, yeah, I better tell you numbers, hadn't I? That wasn't very good. So, well, we'll switch it back to here. Right? Okay, so sliding without, I did put it up there. Sorry, I just got the wrong order. So if we were sliding without rolling, which would reach the bottom first, right? The disc, the hoop, both at the same time, or it's impossible to tell. Wow. Okay. Excellent. Yes, that is indeed the right answer. If you're sliding, there's no rotational kinetic energy, and both of these things have the same mass, and they're dropped they slide from the same height, and so the moment of inertia doesn't matter, and so therefore they're both equivalent, and they will both end up with the same final velocity. Okay, so I've got a couple of minutes, so I will just introduce this last topic that you'll go over on Monday. So the last type of quantity that we introduced when doing linear problems was momentum. So it should come as no shock that there is a rotational form of this, and this rotational form of momentum is called angular momentum. And we write it with the vector quantity L. It's a vector just like linear momentum is a vector, and is equal to the moment of inertia multiplied by the angular velocity. And it gives you a measure of the quantity of the angular motion in a body, just like momentum gives you a measure of the quantity of linear motion in a body. But it is a vector quantity, and this is going to be important right at the end of the rotation module. We do a little bit of stuff with gyroscopes, more qualitative rather than quantitative, but that it becomes important to remember that angular momentum is a vector. So if we take Newton's second law in angular form, we have moment is equal to the moment of inertia times the angular acceleration. And this is equal to I times d omega by dt. And we can rewrite this, since the moment of inertia is generally constant. We have the moment of the force is equal to d I omega by dt. And so we can rewrite this as the moment is equal to the rate of change of angular momentum, right? And if you remember, this is also how we wrote down Newton's second law, which was that force is equal to the rate of change of linear momentum, right? So you can again see that there's an exact parallel. We know that moment and forces are the equivalent in the rotational and linear world, and it's the same here with angular momentum and linear momentum, right? So again, we've got an exact equivalent between linear momentum. Angular momentum is the exact equivalent of linear momentum, and as you'll see on Monday, we also have a series of rules like conservation of angular momentum and so on that you'll be applying on Monday's lecture. Okay, so I'll call it a day there. I won't be seeing you on Monday, but I will see you in a week's time on Wednesday. Objects. We've got one that's a loop, and we've got one that's a disk. Now, as we did last time in the last lecture, the moment of inertia of this ring is mr squared, where r is the radius, right? And the moment of inertia of this disk is a half mr squared, all right? So this disk has got half the moment of inertia of the ring. You didn't have to know the exact formula, all you had to be able to recognize, and we did the question last lecture, so I was completely fair, you knew the answer, was that the ring here has a higher moment of inertia than the disk. Now, if you remember, if we're rolling without slipping, as we do down that ramp, then we have the linear velocity of the center of the circular object, whatever circular object it is, the linear velocity here is equal to r times the angular velocity, right? So if we look at these two guys here, so for rolling at the same speed, they will have the same angular velocity, right? So if the linear speed of these two objects is the same and they're rolling, they will have exactly the same angular velocity, right? Because they've got the same radius. But their rotational energy, kinetic energy, is equal to a half I omega squared. So if they are rolling at the same linear velocity, they will have the same linear kinetic energy, right? So in this case, a rolling object has both linear kinetic energy and rotational kinetic energy, right? So they will have the same linear kinetic energy, but because, if we put this in here, right, we're going to end up with a half times I times r times v squared over, what am I doing? Okay, so here I have omega is equal to v over r, so here I have a half I times v squared over r squared, right? So if I have the two things rolling at the same linear velocity, their linear kinetic energy is going to be identical because it's the mass times the linear speed squared, so no difference there because they've got the same mass. But if I look at the rotational kinetic energy, their linear speed is the same, their radius is the same, but their moments of inertia are not the same. And so therefore, when you're rolling, this hoop that has a far larger, has twice the moment of inertia of the disk, this hoop has, for the same linear velocity when it's rolling, has more total energy. And since the energy that's driving this comes from the gravitational potential energy as they roll down the ramp, right, there is going to be the same energy available to both, but because to have the same linear speed, the hoop has to have a lot more energy. The only thing it can do is rotate more slowly, and so that's why it always loses the race. Because to move at the same linear velocity while rolling, it has to have more energy. There isn't more energy available, and so therefore it has to move more slowly, and so therefore the disk will always win the race. Right? And so that's a little trick. That's a little bit hard to do on a bar, I suppose, and win money off your mates, but it's a little trick guaranteed to work every single time and confuse your friends with. Angular form, we have moment is equal to the moment of inertia times the angular acceleration, and this is equal to I times d omega by dt, and we can rewrite this, since the moment of inertia is generally constant, we have the moment of the force is equal to d I omega by dt, and so we can rewrite this as the moment is equal to the rate of change of angular momentum, right? And if you remember, this is also how we wrote down Newton's second law, which was that force is equal to the rate of change of linear momentum, right? So you can again see that there's an exact parallel. We know that moment and forces are the equivalent in the rotational and linear world, and it's the same here with angular momentum and linear momentum. Right? So again, we've got an exact equivalent between linear momentum, angular momentum is the exact equivalent of linear momentum, and as you'll see on Monday, we also have a series of rules like conservation of angular momentum and so on that you'll be applying on Monday's lecture. Okay, so I'll call it a day there. I won't be seeing you on Monday, but I will see you in a week's time on Wednesday.